In our first several lessons, we looked at properties of vectors, how to find the length of a vector, how to add two vectors, how to scale a vector to change its length, computing dot products, finding the angle between vectors, etc. More computational. Today we're going to take our first look at properties, the behaviors of vector arithmetic. And because we're starting to get a little more formal, we want to introduce some formal notation. We use this symbol Rn to indicate the set of all vectors of length n. And we say a vector lives in this space, it's one of these, by saying U is an element of Rn. So for example, our famous vector now 3, 4 of length 5 lives in, or is an element of R2 because it's a vector with two elements. And the vector 1, 3, 7 lives in R3 because it's a vector with 3 coordinates or 3 elements, etc. And we can make vectors of any length. Vectors in R5, in R17, but for many practical purposes, the ones we'll use live in two-dimensional space or three-dimensional space, or in physics, space-time is a four-dimensional space, x, y, z, and time. Or we'll see other uses where we might want vectors of a bigger length. So this symbol just says it's vectors with real number elements with that many components. Okay, so with that settled, now we want to look at properties that work for any dimension. That is, for vectors in R2, R3, R37, or whatever. So let's assume that U and V are two vectors that live in the same dimension space, n-dimensional space. And you can think for now that that's 3 dimensions or 2 dimensions. And then I want a couple of real constants. We'll call them A and B are just real numbers, the numbers we're used to working with. So given two vectors and two numbers, what's true? Well, here's the first property that's always true. U plus V is the same thing as V plus U. That is, vector addition commutes, or it's commutative operator. It doesn't matter which one I put first. I get the same answer. And remember, we actually proved this geometrically, or saw this geometrically, by the Parallelogram Rule, or the head-to-tail addition rule for vectors. If I take two vectors in the plane and add them, there's U and there's V, or there's V and there's U, the sum is the same no matter which way I add them. Let's see, that's U and that's V. So either way, the sum is the diagonal of that parallelogram. Going this way is U plus V, going this way is V plus U. The answer, U plus V, is the same no matter which way I go. And that's the idea. Well, how do we prove something like this? How do we prove that vector addition is commutative? Well, let's assume for now that the n is 3. I'm going to work in three-dimensional space. And so this won't prove it in every case. You have to do a little more work to show it works for any dimensional space, but assume that U has coordinates D, E, F. That's a three-dimensional vector. and V has coordinates RST. Well, by my law of U plus V, what is U plus V? Well, it's the first element is D plus R. The second element is E plus S. And the third element is F plus T. By my regular rules of vector addition. But what are these symbols, D, E, F, R, S, T? They're just regular old real numbers, the numbers we've been adding, subtracting, multiplying, and dividing for years. So D plus R is the same thing as R plus D. Why? Because real number addition is commutative. Doesn't matter whether I add 5 and 3 or 3 and 5, or 5.6 and 2.1 and 2.1 and 5.6. Real number addition we know commutes. The same is true with the second element. E plus S is the same thing as S plus E. And F plus T is the same thing as T plus F. But now when I look at this, this is exactly the answer I get when I add V plus U. So by my chain of equals, U plus V is this, but the fact that the individual arithmetic operations commute, because these are just regular old real number arithmetic operations, and this is exactly the answer I get with V plus U. I've just proven in the three-dimensional case that U plus V is V plus U. So this is the general idea of how we prove these things, and you'll get practice doing that in class for homework. Okay, well, let's list some of the other important properties of vector addition and vector scalar multiplication. And to do that, I'm going to add a third vector to my collection. We'll call it W. Okay, so what else is true? Number 2. Check my notes, I'll just go in the same order. Vector addition is associative. That is, if I take the vector U and add it to the sum of two other vectors, the parentheses say do this addition first. So V plus W is a vector. If I take that answer and U plus that, I get the same thing, it turns out, as if I added U and V first. And then added W. That's called associativity of vector addition. And the proof is very similar for a fixed dimension like 3 dimensions. I just look at the elements, and it's based on the fact that real addition, real number addition is also associative. So which operation I do first doesn't matter in a chain of additions of vectors. Property 3 is an easy one. U plus the 0 vector gives me just U. That is, the 0 vector acts as the identity, the additive identity, just like the 0 number acts as the identity for a regular real number addition. So notice this is a vector of zeros of the same size as U, not just the 0 number, because I can't add a number to a vector. So this is U of length n, and this is a collection of n zeros that makes up a vector of the same length. And so this acts as the additive identity. Property 4 if I take U and add -1 times U, what do I get? Well, for every element in here, the corresponding element will be the negative of it, and so I get the 0 vector. We say that -1 times U is the additive inverse of U. Because remember, what happens? This points in exactly the opposite direction. So geometrically, what am I doing? I'm taking the vector U, and I'm adding the vector negative u. So of course I end up where I started. And we always start at 0. It turns out, for those of you moving on to higher mathematics, that having commutativity, associativity, and identity in inverses makes this what's called in algebra an abelian group. We're not going to focus on that here, but just so you see the idea in case you go on to higher mathematics. Lots of things behave like this, so this collection of properties is an important set. Okay, now we want to introduce scalar multiplication to the mix after we've considered these additive properties. And we have the following. Number 5. A, consistent with my symbols, A times U plus V. So if I add two vectors together to get a single vector, and then take that answer and scale it by the constant A, I get the same result as if I scale each one individually and then add them. This is the distributivity of scalar multiplication over vector addition. And it works because essentially what I end up doing, remember when I multiply a vector by a scalar, I multiply each of the elements by that. So the elements of U times A are just A times the first element, comma A times the second element. So it works because regular old arithmetic of real numbers, it has this distributive law. Property 6. If I take two scalars, two real numbers, and add them, and then multiply by the vector, that's the same answer as multiplying A times the vector, multiplying B times the vector, and then adding the two vectors as an answer. So here the addition is of real numbers, and here the addition is of vectors. And it's nice that that works out, and it's not hard to prove. Property 7. This is a strange one. I multiply the number b times the vector v, the answer is a vector, and then if I multiply by a, I'm multiplying a by that answer vector. So I'm scaling the vector twice. But it turns out that's the same as if I multiply the numbers first, and then multiply the product of the numbers times the vector. This is called the compatibility of scalar multiplication with real number multiplication. And it makes sense because if I have some vector v and I multiply it by a, some magnification factor, so there's AV, and then I take that answer and multiply it by b, so there's b times AV. This vector is obviously, since I scaled it by a and then scaled it by b, it's AB times longer than the original vector v. So it makes sense geometrically that all I'm doing is scaling twice. Okay, then finally, a very easy property. That we've kind of taken for granted already anyway. If I multiply the number 1 times a vector, I get the vector back, because I'm multiplying each of its elements by 1. So these 8 properties, the first 4 we listed and the new ones, qualify Rn is a vector space. What's a vector space? It's any collection of mathematical objects that have these 8 properties with a properly defined addition and scalar multiplication. Later in the course, we'll look at a couple of other examples of vector spaces that aren't just our regular vectors. So in class, we'll get practice proving a few of these properties, and also why are these useful, seeing why they're useful. They're useful for the same reason that our algebra rules and the real numbers are. By these properties, it lets us solve vector equations.